Hi guys, we're going to talk about redox balancing, and for some of you this may be, familiar to you, and then to others it may be less familiar. So I want you to make sure that we at least go through some examples of each. So remember, when we use the term redox, and you did some reading about this, we're talking about oxidation reduction. So this is a reaction where there is a transfer of electrons, and oxidation, and again, this was from your reading, but oxidation is where you lose electrons, and reduction is where you gain electrons. So inside the chemical reaction, somebody is losing electrons and somebody else is gaining them. And some of you may have learned some of these mnemonics like oil rig. Oxidation is loss, reduction is gain, or my personal favorite, Leo the lion says grr. Loss of electrons is oxidation, gain of electrons is reduction. But this chapter is all about reactions, so we need to talk about balancing reactions because they aren't always as simple as some of the other types of balancing. So the first type, and again, these are talked about in your reactions packet. In fact, pause the video. Get your reactions packet. You don't have to open it yet, just put it handy. Okay, if you didn't pause it, way to go. Nice job. Maybe you're already organized. Anyway, just kidding. Here's the first method. Oxidation states method. This is the first one that your reactions packet talks about, and I didn't have you read these pages in the book because your book does it differently than the way most of you learned it in Chem 1. The packet, however, does it just like most of you learned in Chem 1. So here's the first method, oxidation states method. This is the method that they talk about on page 69 and 70 in the reactions packet. So I'm going to use an example like this. Iodine plus chlorine plus water yields HiO3 and HCl. And we're going to go ahead and balance it, but the key with oxidation reduction reactions is that the electrons must be balanced. The electrons lost and the electrons gained have to be equal. And normally we just make sure the atoms add up. But here we have to make sure the electrons are accounted for. So with the oxidation states method, this is where we look at the oxidation numbers. We mentioned them briefly. There's a page in your book that talks about how to assign them. So we're going to assign oxidation numbers to everybody. Here's iodine, an element by itself, so it's 0. Plus chlorine, an element by itself, so it's 0. In water, we talked about the fact that oxygen is almost always -2, except in a peroxide when it's -1. And hydrogen is almost always +1, so those are easy enough. Now we go to the other side of the arrow. Oxygen again, -2 in a compound. Hydrogen again, +1 in a compound. So now you can assign iodine based on everybody else. Remember, in a neutral compound, the whole thing needs to add up to 0. So you have 6 negatives and 1 positive, which means iodine must be +5. And then in HCl, hydrogen's +1, so chlorine has to be -1. So that's the first step in the oxidation states method. The second step is to figure out who's losing and who's gaining electrons. So I notice here that iodine starts at 0 but becomes +5 on the other side of the arrow. Well, in order to get a positive number, it must have lost some negative electrons, and in fact it must have lost 5 negative electrons. Now I'm going to look who else does something. So I see chlorine starts at 0 and over here it ends at -1. So chlorine goes from 0 to -1. It must have gained a negative electron. That's how it got that -1 charge. Now if we just simply look at who's oxidized and who's reduced, Leo the lion or oil rig, Leo, loss of electrons is oxidation. That means this is the oxidation. Gain of electrons is reduction. That means this is the reduction. And if we think about what is really reduced, why is it called reduction if it's gaining? It's because, look, the oxidation number starts at 0 and it's reduced to -1. That's the reduction part of it. Here's the key. You need to use the least common multiple to make sure that the electrons are balanced. So I have 5 electrons lost and 1 electron gained. So I'm going to multiply them both by something. I can multiply this one by 1, and I can multiply this one by 5. That makes 5 electrons lost and 5 electrons gained. That tells me, this number tells me how many of each atom I need on both sides of the arrow. I need 1 iodine on each side, and I need 5 chlorines on each side. All right, so I come over here, and I need a coefficient. And that coefficient, I need 1 iodine, but they're in pairs. So if I take a half of an iodine, I'll get 1 iodine there. On the other side of the arrow, if I just put a 1 in front of this, I get 1 iodine. I'm only looking at the iodine. Then I look at the chlorine. I need 5 chlorines on both sides of the arrow. That's easy over here. I can just put a 5 and then I get 5 chlorines. On the left side though, again, they're in pairs. So 2 times what gives me 5? 2 1/2 or 5 halves, so I can put a 5 halves. That will give me 5. Now, I want you to notice that water has no arrows attached to it. And if that's the case, and there's no arrows, anything with no arrows attached to it isn't being oxidized or reduced. So you're going to hand balance it. You're going to literally, just like the old way, look at it and decide how many of those you need. But before you do that, we know we can't leave these fractions in there. So let's double everything to get rid of the fractions. So then it becomes 1 iodine plus 5 chlorine, plus, I don't know how many waters because I'm going to hand balance that, plus now I'm doubling these, 2 HiO3 plus 10 HCl. Well, let's see how many we need. Oh look, there's 6 oxygens, so I probably need 6 of these. That gives me 12 hydrogens and 10, yay. And if I actually check this, you know, I've got 10 chlorines, 2 iodine, 2 iodine, it's balanced. So that is the oxidation states method. That's the first one. All right. Pause, get a drink, whatever you need. But open up your reactions packet right now, pause it if you need to page 70, because I am not going to write some things out, but I'm going to assume you can stare at them while we work, and so I need you to open it up. I need you to look down at the bottom of the page where it says ion electron method in acidic solution. It's at the bottom of page 70. It goes onto page 71, and they actually have this method in 2 ways. On page 70 it's in acidic solution, and at the bottom of page 71 it's in basic solution. Most of you called this, and I will too, the half reaction method. We're only going to look at the one that says in acidic solution, and it goes 1 through 8. 8 is on the top of page 71, and I want you, so that this method could be used for both acid and base, I want you to write in step 9. So at the top of page 71, underneath number 8, write in step 9. Here's what I want it to say. If in basic solution, add enough OH minuses to both sides of the reaction in order to cancel the H pluses. Reduce as necessary. I will show you what that means, and I will show you what all the other steps mean by doing an example with you, but make sure you write in step 9. Step 9 is one that you only use if you're told it's in basic solution. So you won't always use step 9, but sometimes you will need to. So let's do an example together. Keep those pages open because I'm literally going to walk you through those steps that are listed there and talk you through it. So here's an example. NO3 minus plus Br minus yields NO plus Br2. And here's a problem where you literally cannot balance this the way that you used to. It is missing things, and the This method will allow you to put those things back in. All right, so we're going to look at this step by step. Step 1 says assign oxidation numbers to each atom in the equation. All right, honestly, step number 1, you don't really have to do step 1. It's handy so you can identify who's reduced and oxidized, and so that you can write the half reactions, but the oxidation numbers themselves are not crucial in this. But we'll go ahead and do it just for good practice. So this is -2. Since the whole thing, now here's an example where it's not going to be neutral when you add the oxidation numbers, it's going to have a negative charge. So this one must be +5 to account for that. Here's another example for oxidation numbers. If you have an ion of one element, the ion gets its charge, so this must be -1. Over here, oxygen's -2, so nitrogen must be +2. And here's an element by itself, so it's 0. All right, step 2 on the bottom of page 70 says identify what is being oxidized and reduced. So I look at this and go, hey, nitrogen's going from +5 to +2. That's a reduction. The charge went down. And look, bromide goes from -1 to 0. Charge went up. That's an oxidation. The reason that you need to just identify that is to get into step 3. Divide the skeleton equation into 2 half reactions, the oxidation and the reduction. So this is why it's called the half reaction method. I'm literally going to separate it into the oxidation and the reduction. It doesn't matter which one you write first, and so that's why it's not super crucial to label oxidation and reduction. I just did it to show you. So that's step 3. I wrote the half reactions. Step 4. For each half reaction, balance atoms other than H and O. So balance everything except for hydrogen and oxygen. The nitrogens in this one are balanced, but over here we've got 2 bromines in one, so I'm going to balance that. Okay, I'm done with step 4. Step 5. For each half reaction, balance the oxygen by adding water to the side that needs oxygen. Let's stop there. All right, so I look at this top one and we have 3 oxygens in one, so I'm going to need 2 waters because I balanced my oxygens by adding water, which means I've now screwed up the hydrogens, so we keep reading. Rest of step 5. And balance hydrogen by adding H plus to the side that needs H. There's nothing in this bottom one, but over here I've just added 4 hydrogens, so I'm going to balance those by adding H plus. All right, I'm done with step 5. Step 6. For each half reaction, oops, I lost my page, there we go. For each half reaction, add up the total charge on each side and add electrons to balance the total charge. Okay, let's do that. So literally on this side, I have 4 positives and 1 negative, so my overall charge here is +3. On this side, NO is neutral, water is neutral, so this side is 0. I'm going to add electrons to make these numbers be the same. And electrons, of course, are negative. So I'm going to need 3 negatives, and I'm going to add them to this side. That way the 3 negatives and the 3 positives equal 0. I'm going to do the same thing on the bottom. This side, I have 2 negatives. And over here, I have 0 because it's an element by itself. It's neutral. So I'm going to add electrons to make both sides be equal. I'm adding negatives, so I'm not going to add them to this side because that would make it more negative. So plus 2 electrons. That gives me 2 negatives over here and 2 negatives over here. We're good. That's step 6. Step 7. Balance the number of electrons being lost and gained. So I'm literally going to, again, find the least common multiple. I'm going to multiply this one by some number, and I'm going to multiply this by some number, so that 3 electrons and 2 electrons, so that we get the same number. So the least common multiple is 6, so I'm going to multiply this one by 2 and this one by 3. I'm going to rewrite these because it's a kind of a mess right now. So I have 6 electrons. I'm multiplying through, plus 8H plus 2 NO3 minus yields 2 NO plus 4 water. And on the bottom one, I have 6 Br minus yields 3 Br2 plus 6 electrons. Now, step 8. Add the 2 half reactions and cancel anything that's the same on both sides. Sometimes there's multiple things to cancel. In this example, the only thing that's the same on both sides are the electrons, and your electrons have to cancel or you screwed up. If you screwed up, start over. Don't try to find your mistake. It's so hard to do that. Nothing else here cancels out, so my final answer is 8H plus 6 Br minus it doesn't matter what order you write these, as long as the things on the left side of the arrow are on the left and the things on the right side of the arrow are on the right. Makes no difference. And if all goes well and you know that everything worked out, you should have the same number of hydrogens, bromines, nitrogens, and oxygens, and we do. And your charge should also balance. So the overall charge on this side, 8 positives, 6 negatives, 2 negatives is 0, should balance the, oh sorry, that's 2, should balance the overall charge on this side. They're all neutral, it's 0. So there's a couple of checks that you can do to help you ensure that you did it right. The only other thing I want to mention then is what to do with step 9, because in the example I originally gave you, I mentioned nothing about happening in a base, and that step 9 that I asked you to write in said if in a base. So here's the example. I'm actually going to use the very same example, but I'm going to write it differently. So what if it was written like this? In a base. And you will be told if it's in a base. You don't ever have to guess that it's in a base. You'll be told. What you do is you go through, and really, because steps 1 and 2 aren't completely necessary, so go through steps 3 through 8. We did that already. And get your answer for steps 3 through 8. That's this thing here. I'm going to just rewrite it for the sake of this. So we went through steps 3 through 8. We got this as our answer, but it's in a base, so we have to do the last step. And that last step is the base step. So the base step says, if in a base, we're going to add enough OH minuses to cancel the H pluses. So we have 8 H pluses. So what we're going to do is we're going to add 8 OH minuses to cancel them, because OH minus and H plus make water, and so this becomes 8 water. But if we do it to one side, we have to also do it to the other, so I'm going to add 8 OH minuses to that side as well. That's the step. Now we just have to do a little bit of reducing, because if these turn into 8 waters, I have 8 waters here, but I have 4 over here. So I'm going to cancel that. So 4 of the waters could cancel 4 of the 8, leaving 4 behind. And so now just to rewrite it to make it neat, it becomes 8H2O plus 6 Br minus plus 2 NO3 minus yields 3 Br2 plus 2 NO plus 8 OH minus. Okay, it's easy to watch me do it, but you know you're going to have to practice you doing it, and that will be coming up.